面有请来自红帽 RadosGW 软件开发工程师 Orit Wassermann 和 Benjamin， 他们的主题是这里有关于 RadosGW 你想要知道的一切。大家欢迎 Let's welcome RadosGW developers Orit Wassermann and Benjamin. Their speeches is about everything you wanted to know about RadosGW.
Hello, I'm Orit Wassermann. I've been RadosGW co-developer for the last 3 years, and this is Benjamin, who's been also RadosGW lead at Red Hat for 3 years. And today we're going to talk about RadosGW. I will start with giving some overview about object storage, a little bit RadosGW internal and cool feature, and then Matt will talk about our future plans for Mimic and beyond. So what is object storage? So it's something between block storage and file system. And it was designed for large scale, large number of objects, and also a large amount of data. We have a flat namespace. Objects are organized in a bucket or container, and buckets cannot contain other buckets, so we have one level. But if you need to preserve some hierarchy, you can actually use a prefix to the name and have a virtual hierarchy. Objects have very rich metadata. We have ownership, access control list, and user can add its own metadata to the object. It can add key values pairs to the object. So if I want, I can decide I want to color all my objects and put them like they are red or blue. Or if it's my photos, I can add some metadata that contain the people who are in the photo. It has very rich authentication. And one very important feature, objects are immutable, which allows the object storage to scale so much. What it means that when you change an object, you have to write it completely. You cannot write only the change you need to the object, but you can read parts of the object. You don't have to read all the objects. Now we're going to talk about very nice features object storage has that make it very useful. But first we're going to talk about cloud object storage. So object storage was invented way long before the cloud was there. But it didn't catch up. People use block and file, but what changed is that we got the cloud. And when Amazon first started the cloud, they had their object storage called S3, and what they added is the way we access the storage. We use REST API, and that is the natural way to use data in the cloud, and since then it grows, and cloud storage is very popular, and especially S3. One thing we need to write to the storage, and in object storage we call it upload because we use HTTP. And we need to upload very, very large objects. We need to handle cases where we have a network error, and for that we have a different way to upload the object. It's called multi-part upload. And what it means, we take a big object of 1 giga and we divide it into parts, and we upload each part separately, and only when we're done and we're sure all the data is there, we complete the upload, and only then the object will be created. If something happened and we didn't complete the upload, the object storage will actually clean all the temporary data we stored. It helps them to recover from network error. So if I divided the object to 4 megabytes, and in one chunk I failed, I can just upload it. I can stop and resume later. I can even upload an object I don't know its final size. I can use it, for example, for streaming video. And I can use it for transaction. If in a file system we would create a temporary file and then we name it, that is very, very expensive in object storage because there's no rename. We access the object by its name. So it's actually copying the data and deleting the old object. I can use multiple upload to actually do a transaction like. I will upload and do a multiple upload to the temporary object, and when I want to finalize the transaction, I will complete it. One very important comment is that there's a cost for multiple upload, and if your object is small, you should not use multiple upload. I've seen up to 2-3 times slowness if you use multiple upload for small objects. Another very cool feature is versioning. Versioning is enabled per bucket, and by default it's disabled. When we enable in a bucket versioning, every time we overwrite an object, it won't be overridden, but the object storage will create a new object with a different version. This way, for example, if I upload my document revisions, I can have the old revision and go back in case I want to restore old version. The main problem in versioning and why it's not enabled by default, that it wastes space and space is expensive. So for that we have actually lifecycle, which is an automatic way to do object transition. The most common one is expiration. I can say I want this old some date or usually age, and the object storage will delete object automatically. I can say I don't want to keep, let's say it's a version bucket, I don't want to keep objects that are older, versions that are older than 6 months, and the object storage will automatically delete those old versions. I can use it also for tiering. So I can say if I have objects older than 2 years, I want to move them to a colder tier, less expensive. At the moment, RadosGW doesn't support tiering, only expiration. Now we're going back to Ceph and RadosGW. You've seen this slide several times today. And RadosGW, like the other services Ceph provides, uses libRados to store all its data and metadata in Rados. We want to be able to scale up, so RadosGW is almost stateless. And in case you need more throughput, you can spin a new instance of RadosGW on the same Ceph cluster, and they will serve the user the same data. We need to support REST APIs, so that means we need to have HTTP server. There are 2 ways you can use RadosGW. We have an embedded web server called Civic Web, and you can use FastCGI to use an external web server like Apache. We use Rados, but Rados objects are limited inside. The default is 4 mega. We're talking about object storage, and we're talking about really, really large objects. The limit, for example, in AWS, and we also use the same default, the biggest object you can upload is 5 terabytes. If you want to just do a regular upload, then it's 5 giga. Those are big, big objects, and that means we need, each object will probably be from several Rados objects. So every object has an edge object. It's one Rados object. It contains all the object metadata, its access control, and its manifest. And we still have some room to keep data. So small objects are actually one Rados object. Bigger objects will be striped to 4 megabyte chunk, and those we call tail objects. If we talk about naming, the head object is very fast. If you know the bucket ID and the object name, you can access the head object quite quickly. We need to use bucket ID and not bucket name because there are corner cases when you create and delete a bucket, and a different user can create a bucket with the same name, and we need to identify those. And the tail objects also have a very simple naming convention. So when we, for example, read, we can know which tail object we need and read it quite quickly with one modest read operation. Object storage requires us to index the bucket. What we user needs is to, when he lists the bucket, you want to see an order list of all the objects in the bucket. That is the bucket index. It's an object, an OMAP Rados object that contains a list of all the objects in that bucket. But we talked about large scale, and we can have millions, and actually I saw billions of objects in the bucket. So one OMAP Rados object cannot handle that load. So Yahoo helped us and added bucket index sharding. So when you create a bucket, you can say how many shards you want for the bucket index, and it creates several OMAP Rados objects to handle the bucket index. But it was static. You don't always know how many shards you want in a bucket. You can think, I will need only 100, and in the end the bucket will grow and you need more. In Joule, you added off-memory sharding, which allow a user to change the number of shards a bucket index uses. In Luminous, we have on-memory sharding, which means you can manually reshard the bucket and increase its number of shards. And we also have dynamic resharding. RadosGW checks periodically the number of shards of a bucket and its number of objects, and when you see that it's not good and you need to increase it, we reshard the bucket automatically. Sadly, multi-site and dynamic resharding don't play well together at the moment, but we're working on fixing that. So for multi-site, you cannot use dynamic resharding. For every time we access the storage, we use an REST API. That means the first thing we have to do is to authenticate the request. For that, we need the user information, its key, its secret. We also need the bucket endpoint to convert between bucket name and bucket ID. And the bucket instance information contains, for example, the number of shards for the bucket index and other information. But we want performance. If every time each one of them is a Rados object, we'll read those, we'll waste performance, so we cache them. That's the RadosGW metadata cache. We usually have several RadosGW running on the same data. We have to synchronize them. We are distributed. For that, we use watch notify. Rados provide us. Every time a RadosGW changes one item in the metadata cache, the other RadosGW will get a notification and know to invalidate the cache. In the last few months, we have noticed some problems with coherency of the cache and its performance, and there's lots of work that Matt's going to talk about of improving it. A very important feature we need for storage, because we care about the data, is disaster recovery. We want to have a copy of the data in case we lose our data center in some disaster. It could be actually also a bug. For that, we have Replication. Replication allows us to replicate the data between different Ceph clusters, remote Ceph clusters, and because of that, the data replication is completely asynchronous. We have small number of metadata operations that are synchronous, but they happen not frequently. Like, for example, adding new user, deleting a user, creating a bucket, or deleting a bucket. Those are synchronous. You can configure the replication to be active-active and active-passive. And in Luminous, you can disable and enable a synchronization per bucket. Up to Luminous, we would replicate full zones, but now you can have better granularity. Also new in Luminous is metadata search. We have the user metadata, but user wanna have a list of all objects that have those metadata. if I talked about photos, I want a list of all my photos that have my daughter in it, so I can create an album. Or maybe I want a list of my photos for some trip. This is for that metadata search. But we are a storage system, not a search engine. So we use Elasticsearch, which is a very good search engine. We export our metadata into a different cluster that Elasticsearch can access as its backend, and the user queries are executed in Elasticsearch, and then he gets the list of the object he wants. We also have NFS. NFS is a file protocol, but we have NFS on RadosGW. We have a library called RadosGW, which is like an instance, a full instance of RadosGW, but without its front end. And it also has a layer, RadosGW file, that converts between object operation and file operation. For NFS, we use NFS Ganesha to implement the NFS protocol. So you run an NFS Ganesha process with RadosGW, and then you can access RadosGW using the NFS protocol. This is very useful if you have legacy application that needs NFS, but the rest of the application use S3, and if you want to export your data from NFS into RadosGW. In Luminous, we also added support for bucket and user policy. Access control lists are not enough. We want much better granularity. We want to share data between different buckets, between different users. For that, we have bucket and user policy. We can allow access from different accounts to the same data. You can have anonymous users. You can restrict actually access to a list of specific IP. It's very important to keep your data safe. Actually, I think last week or maybe 2 weeks ago, Walmart diamonds or something, or jewelry, had a public bucket in AWS. Public bucket in AWS S3 means everybody can access the data. So it's very important to make your data safe. We have a lot more new in Luminous. We have server-side encryption for the objects. We have compression to save data. And we have object tagging, which is the enrichment of the metadata search in object metadata. And now Matt will continue and talk about Mimic.
I think I mean that. Okay, so this isn't going to be a picture of it, especially because the Beyond is here. It's not going to be every possible thing that we're working on. This is RadosGW is one of the richest ecosystems in Ceph, with lots of people working on it, and lots of them are here. Pardon? Slower? Okay, I will try. So there's a lot of development happening in Ceph RadosGW that's not going to be here, but we're going to concentrate on the things that are definitely happening in Mimic and that are areas of emphasis right now for us in the post Mimic timeframe. Probably one of the biggest pieces of work being undertaken right now is Cloud Sync, and there was actually an excellent talk on that topic earlier this afternoon. There are two primary contributors. Yehuda Sadeh is our upstream architect. He's been involved in inventing this feature and building it on the foundation of multi-site replication, and others have joined in. The uCloud work, adding their cloud synchronization capabilities to the same interfaces is ongoing. But the idea here is that the foundation of multi-site replication is extended to allow replication transactions into and out of various public clouds or other private cloud representations that are different from RadosGW. So you can combine your data that's in an RadosGW cluster on-premise with data in a public cloud that's off-premise. And eventually it's even conceived by Yehuda that we may have the ability to synchronize data between independent non-RadosGW data sources and data sinks with various policies. And the work already in progress not only allows you to move data from an RadosGW cluster into a similar representation in a public cloud, but it allows it to be various transformations of the representation to allow, for example, all of the objects in all the buckets or a subset of buckets to be represented in some other subset of buckets in the other source or in the sink, etc. Presently, we have a unidirectional sync, but a bidirectional sync is being worked on. A key area of focus for us in Mimic and immediately post-Mimic is scalability, and both scaling up and scaling down. And as Orit mentioned, we currently support two HTTP front-end options, although others can be developed. The original implementation was using fast CGI and allowed you to plug in various web servers, but it has some protocol inefficiencies, data copying, and so forth. And to solve that, a native web server based on an open source project called CivicWeb was used. It provides a tight integration with the RadosGW code base, but it has a number of limitations that have surfaced over time. The big one being that it uses a thread per connection request model, which limits the number of HTTP connections that can be realistically served by a single RadosGW, and it's one of the things that's causing sites to need to have a large number of RadosGWs in a cluster in order to scale. In a Hadoop or a massive client workload, there may be a need for thousands or tens of thousands of HTTP connections to be serviced simultaneously, and you shouldn't have to have 10 or 20 RadosGWs to do that. So the solution to that that is currently being worked on most aggressively is a new asynchronous front-end called Beast. This is a strategy similar to the CivicWeb model, but it uses Boost ASIO, a very well-known programming framework for asynchronous TCP sort of application development. That's part of this. That's part of the Boost C++ APIs, and new work from the Boost community to develop a full-fledged HTTP implementation that cooperates with that. And we've used that to build, Casey Botley and others in our team have been building this a new front end that is no longer using a thread per connection processing model at all. It's completely asynchronous. The intent here is to go considerably, is to scale the number of the connection density and on the front side, but as well to in fact reorganize the somewhat similar but less ambitious to the efforts to refactor the OSD. A similar effort is going on around in this mechanism to refactor and reorganize the internal request processing pipeline of RadosGW to be more efficient. Currently, in addition to having a front end that is relatively decoupled from an asynchronous back end, and essentially inducing a top half and bottom half scalability issues in the server, and lots and lots of POSIX threads in use. The new model, the intent is to fully reorganize that into a small number of cooperating threads that use cooperative multitasking to remove context switching and thread transitions between the top half and bottom half. There will only be one half, as it were. And secondarily, we're introducing a scheduler. With the intent that in addition to handling large numbers of connections, we'll be able to manage the incoming workload much more intelligently. We'll be able to classify it into a variety of buckets. For example, read versus write, prioritize traffic with specific criteria over other traffic. In a present-day RadosGW environment, to be honest, it is possible for example, a very aggressive set of clients with high RTT or simply competing aggressively for the resource to, for example, fill up all available work slots with heavy writes and uploads and large object uploads, and in that environment, the server becomes less responsive for other work. The solution is quality of service management, and the schedulers work as part of this process is intended to deal with that. This work is far advanced. There's already an experimental front end in Luminous, and it's already been shown that the existing Beast front end that's in Luminous and Master is, for example, a lot more efficient and much more performant for example, HTTPS processing than the CivicWeb front end. And work is now ongoing and fairly far along to implement both the scheduling and a bunch of the foundational work for the new request pipeline. There are people. A couple of the authors of some of those pieces are here. So if you're interested in talking more about that, you're welcome to do that. We encourage you to do that. And if there's folks that might be interested in working on this part of the code, there's a lot of work already in place, but there's also lots more to do. So this is a good place to be helpful. Another area of pure scalability that we've targeted for work in this development, next level of development cycles is the bucket index itself. The bucket index scaling strategy, as Orit explained, is all about sharding, and it works very well. But there's a problem of competition between workloads that are inconsistent and operating on the indexed store, the OMAP index store underneath the bucket index. And in particular, workloads that are doing enumeration in key order are less efficient than simple get-put workloads that are operating in sort of a perfect efficiency on the bucket index. And our goal is to substantially improve that in two ways. One, we came up with a shorter-term approach. There's a fair amount of inefficiency in the RadosGW server processing. The continued requests across shards, that could, for some workloads, we believe can be ameliorated by relaxing the requirement to enumerate the entire region of the key space in total order. S3 and Swift specify that it will be, but many workloads only require that they see all the objects, not that they see them in a specific order. At in each shard, the natural order, the keys are already in a partial order, but across shards they're not. And by relaxing that slightly, through an API extension, we have the ability to for example, reduce the workload cost of custom workloads that applications are actually generating if they're able to use a slightly extended version of the API, but also in our internal processes like the object lifecycle processing that it has to enumerate all the contents of a particular bucket and doesn't care about the order, only cares about a decision criteria to expire or transform it. But moving past that, we need to do more, and there's also work ongoing. It's at the experimentation stage now, and we're proving various concepts. But we recognize the need to have a more flexible bucket index organization that is not opposed, basically repeating independent orderings at all the shards. So there's work ongoing now to implement a complete reorganization of the bucket index strategy that transforms the shards basically into partitions that contain flexible ranges of objects in total, and such that the entire range across all shards is in key order. The plan now is using numerical methods to construct a candidate partitioning for a particular set of data. The idea is to do it mostly after the fact, once we have a bunch of data that so we can look at the actual keys and use and therefore do that partitioning in a way that's sensitive to the data. But it's also believed that for particular kinds of workloads that may be well known, for example, certain kinds of Hadoop S3A type of workload where we know what kind of keys are going to be generated and what the data set is, we may be able to predict a partitioning that will work well and to do an initial sharding based on that. So, and again, there'll be some sort of analysis that happens infrequently to detect when the distribution of keys across the partitions is relatively imbalanced, and a resharding step, the resharding we already have in place, used to rebalance all the keys. As Orit also mentioned, we discovered sometime in the last year that there were a number of issues with the consistency of the metadata cache in some configurations and for some workloads with a large number of RadosGWs. Of course, lots of as Orit also mentioned, it's more or less typical to have lots of RadosGWs and use at least several. So this is a critical concern for many sites. In the first round of work, a large amount of workload testing and analysis was done Some of it by two members of my team. Adam Emerson, who's in the back there, is a part of this, and another colleague named Eric Avancic did some, and also a colleague of Reitz in Israel, Mark Hogan, did work on this. But one, we did pure cache consistency bug fixes, and a number of, it was discovered that one source of problems was in various retry paths when a cluster is extremely busy, and many of those have been addressed. A second round of work was by what has been done primarily by Adam Emerson that aims to raise the level of consistency program, more at a theoretical level. It's believed that one source of inconsistency that's more or less unavoidable in the current design is in the presence of network partitioning or network inconsistent network behavior between the RWs and operation could be alleviated in two ways. One, there's new logic in being worked on to simply increase the number of to introduce synchronous in-band retries in the case when an RadosGW detects that a synchronous update that is performed through the watch notify mechanism has not succeeded. But more interestingly, we propose, and there's an upstream PR if folks are interested to look at it. We propose the notion of versioning the cache. And allowing the RadosGWs participating in a group to be aware of the current version of the cache that's controlled, that is authoritative, and discard their cache if they're out of date. The idea here is that this will propagate out into the HTTP environment through, and so in other words, into load balancer clusters or similar mechanisms, and propagate back to all the RadosGWs. Even if their internal watch notified communications are interrupted, if the front end traffic is still reaching them, essentially still connecting traffic from different RadosGWs, an RadosGW that has been isolated will recognize when its cache epoch is invalid, and we'll be able to reestablish it, and in that case won't return to clients incorrect data. So that's kind of the scale out broader view of scaling problems we're working on. We're also trying to help and cooperate as best we can with the Rados core team to improve the per OSD performance of indexed operations, which is called OMAP in Ceph, Rados, and a couple of things are going on there, primarily through the work that's been going on by Mark Nelson and others in the Rados team. One involves the work that's already been performed and I believe merged into upstream Ceph, is column family isolation. This is attempting to decouple inside of the RocksDB backend for OMAP workloads that are part of application updates and indexing operations such as RadosGWs from ones that are key value operations that are being used by the OSD itself. Okay. I don't think there's very much more to say, but if people are interested in asking more about this, I'll bring more into it. But suffice to say, there's work going on inside the RadosGW OSD, or sorry, the Ceph OSD to attempt to improve OMAP performance. I think this is the last slide. A final point. There's been work ongoing for the last year and a half or 2 years to implement Amazon's security token service, which at some level is a Kerberos-like integration of token-based authentication that has a couple of purposes. One is to integrate strong authentication with directory services like Active Directory, but in the current phase of development, what we're trying to do is implement to improve the quality of service for Keystone and LNAP users of RadosGW, a token service that is a bit similar to Keystone's V1 auth, which will allow S3 clients whose RadosGW implementation is using Keystone or LNAP as the authentication source to have first-class request signing, which will include the ability to use WSP4, which they can't presently.
Thank you.